To comprehend the monumental shift currently underway in the global solar energy industry, one must first understand the fundamental laws of physics that govern how sunlight is converted into electricity. For more than half a century, the entire photovoltaic sector has been chained to a strict theoretical boundary known as the Shockley-Queisser limit. First articulated in 1961 by physicists William Shockley and Hans Queisser, this limit defines the absolute maximum thermodynamic efficiency that any conventional solar cell containing a single p-n junction can achieve. The existence of this limit is not a failure of engineering, but rather a rigid consequence of the nature of sunlight and the atomic properties of semiconductor materials.
Sunlight is not a uniform stream of energy. It is a complex spectrum of electromagnetic radiation consisting of photons that carry varying amounts of energy, ranging from low-energy infrared light to high-energy ultraviolet light. When designing a solar cell, scientists rely on a specific physical property of the semiconductor material known as its bandgap. The bandgap acts as an energy threshold. If a photon strikes a standard silicon solar cell with an energy level lower than the silicon's bandgap, the photon simply passes through the material undisturbed, generating absolutely no electrical current.
Conversely, if a highly energetic photon, such as those found in blue or ultraviolet light, strikes the silicon cell, the material can only absorb a specific amount of that energy, equivalent to its bandgap. The remaining excess energy cannot be captured as electricity. Instead, it is instantly dissipated into the surrounding environment as thermal heat. This unavoidable phenomenon creates an inescapable thermodynamic bottleneck. Shockley and Queisser demonstrated that because of this spectral mismatch, where low-energy photons are lost entirely and high-energy photons are largely wasted as heat, a standard single-junction silicon solar cell can never convert 100% of the sunlight it receives into electricity. Under normal, unconcentrated solar conditions, the theoretical peak efficiency for these single-layer cells is rigidly capped at just under 34%.
The researchers noted that as the ratio of the cell's open circuit voltage to its bandgap voltage approaches 1, the open circuit voltage effectively drops to 0, which explains the well-documented real-world phenomenon where solar panels rapidly lose their operational efficiency as they heat up in the midday sun. While theoretical limits provide a mathematical maximum, the harsh realities of physical manufacturing impose even tighter constraints. When accounting for unavoidable real-world losses, such as the physical reflection of light off the surface of the glass, the incomplete absorption of photons within the material, and the electrical resistance encountered at the metallic contact points, the realistic, practical ceiling for standard single-junction silicon cells is universally accepted to be approximately 29%.
For decades, the collective might of the global scientific community and hundreds of billions of dollars in industrial capital have been solely dedicated to inching silicon closer to this 29% barrier. Fascinating experiments have attempted to circumvent these thermal losses by utilizing extreme environments or exotic physical structures. For example, a joint research group consisting of Chinese and American scientists recently claimed to have achieved a staggering power conversion efficiency of over 50% in a single-junction N-type solar cell. However, this astonishing result was only achieved by completely inhibiting the conversion of light into heat at temperatures of 30 to 50 Kelvin, an environment just a few tens of degrees above absolute zero. While scientifically profound, maintaining near absolute zero temperatures is entirely impractical for commercial power generation. Other laboratory efforts have explored utilizing microscopic nanowire structures instead of standard bulk silicon. Research has demonstrated that silicon nanowire cells can slightly reduce the reverse saturation current density, leading to a fractional increase in voltage and light absorption. However, the resulting efficiency gain over a standard bulk device was merely a fraction of a percent, moving from 28.09% to 28.22%. These minute, hard-fought fractional gains perfectly illustrate the core problem.
traditional single-junction silicon is hitting a theoretical and economic wall. The industry requires a fundamental technological pivot to maintain the aggressive cost reduction trajectory demanded by the global energy transition. Despite the impending physical limits of the material, the global solar industry remains fundamentally reliant on a sprawling, highly optimized infrastructure built entirely around the crystalline silicon wafer. The scale of this manufacturing apparatus is almost beyond comprehension, and it is the primary engine dictating today's global energy prices. To understand the momentum of this industry, one must examine the rapid internal evolution of the silicon cell itself, specifically the aggressive global transition from legacy P-type silicon to advanced N-type silicon architectures.
Until very recently, the industry standard for solar energy generation was the P-type PERC, passivated emitter and rear cell solar panel. P-type silicon is manufactured by doping the silicon crystal with boron, creating a positive charge carrier environment. In 2021, P-type PERC panels held over 90% of the global market share. However, P-type silicon suffers from a critical flaw. It is highly susceptible to light-induced degradation, a process where the boron reacts with trace oxygen in the silicon, permanently reducing the panel's ability to generate electricity upon its first exposure to sunlight.
To squeeze the absolute maximum performance out of the silicon before hitting the Shockley-Queisser limit, the global manufacturing base has initiated one of the most rapid and expensive industrial retooling efforts in history, transitioning away from boron-doped P-type cells toward phosphorus-doped N-type cells. N-type technology, primarily utilizing advanced structural architectures like tunnel oxide passivated contact, TOPCon, and heterojunction technology, HJT, fundamentally eliminates light-induced degradation and offers significantly better performance in high-heat environments.
The transition has been breathtakingly fast. N-type solar panels surged from capturing just 15% of global solar cell production in 2023 to an overwhelming 69% by 2025. By early 2026, analysts confirmed that N-type technologies commandeered over 60% of total global production capacity, while dedicated P-type PERC manufacturing was rapidly fading into obsolescence, projected to be largely phased out by 2027.
The justification for this massive global manufacturing pivot lies entirely in the long-term economics of energy degradation. While N-type panels carry a slight premium in upfront pricing, their real-world performance gains are undeniable. Independent testing by institutions such as the National Renewable Energy Laboratory has demonstrated that N-type panels consistently generate 8 to 12% higher power output under standard conditions, and up to 20% superior performance in low-light environments compared to their P-type counterparts. More critically, N-type panels degrade at a significantly slower rate. A standard P-type panel degrades by roughly 0.8 to 1% per year. After 25 years in the field, a P-type panel will retain only 75 to 80% of its original nameplate capacity. In contrast, N-type panels degrade at a remarkably low 0.4 to 0.5% annually. After a quarter century of operation, an N-type system will still operate at 85 to 90% of its original capacity. For the general public, a few percentage points of degradation may seem trivial, but at the scale of utility power generation, the financial implications are staggering. If a commercial energy developer installs a standard 1 megawatt P-type system, that system will generate roughly 800 kilowatts of power in its 25th year. The exact same 1 megawatt installation utilizing N-type silicon will generate 850 to 900 kilowatts in that same year. Over the 25-year lifespan of a standard utility contract, this variance equates to massive discrepancies in total energy yield. Data modeling shows that a standard P-type installation might generate 310,000 kilowatt hours over its life, while an equivalent N-type installation will generate 345,000 kilowatt hours.
an additional 35,000 kilowatt hours of clean energy, representing an 11.3% total increase in generation from the exact same physical footprint. For a large-scale 100 megawatt solar farm, this efficiency retention translates to an extra 1.2 to 1.8 gigawatt hours of electricity every single year as the panels age.
Assuming a wholesale electricity price of 10 cents per kilowatt hour, the slower degradation of the N-type silicon yields an additional $120,000 to $180,000 in annual revenue for the solar farm operator in the later years of the project.
Consequently, major panel manufacturers confidently offer warranties stretching 30 to 35 years for N-type products, far exceeding the standard 25-year guarantees of older technologies. To meet the surging global demand for these highly efficient N-type wafers, manufacturing scale has expanded to unprecedented levels, primarily concentrated within the People's Republic of China. Chinese manufacturers dominate the global supply chain by an extraordinary margin, producing over 96% of the world's silicon wafers and over 92% of all finished photovoltaic cells. To differentiate themselves in this fiercely competitive market, leading Chinese conglomerates are building vertically integrated megafactories that defy traditional industrial scales. For example, Jinko Solar recently commenced construction on a massive 56 gigawatt vertically integrated manufacturing facility located at the Xiaoxiao River Industrial Park in Shanxi, China. This single four-phase facility is designed to consolidate every critical step of the solar manufacturing process, from pulling the raw silicon rods and slicing the wafers to fabricating the advanced N-type cells and assembling the final modules entirely within one massive geographic footprint. By optimizing logistics and minimizing transportation costs between manufacturing stages, these mega facilities continually drive down the wholesale price of solar panels, allowing developers across the globe to deploy solar energy at rates that were financially impossible a decade ago. The deployment numbers reflect the success of this massive industrial infrastructure. Global photovoltaic additions reached over 2 terawatts of cumulative installed capacity by the end of 2024, with new annual installations estimated between 554 gigawatts and 602 gigawatts. In the United States alone, solar power became the second largest source of new generation capacity. The United States installed over 36 gigawatts of alternating current photovoltaic capacity in 2024, representing a 34% year-over-year increase. In states like California, solar energy accounted for an astonishing 32.4% of the state's entire electricity generation. However, despite these staggering deployment figures and the billions of dollars invested in the transition from P-type to N-type silicon, the fundamental physics of the Shockley-Queisser limit remain unyielding. Advanced N-type TOPCon and HJT cells are currently achieving efficiencies ranging from 23 to 26% in mass production. As these panels edge ever closer to the 29% absolute physical ceiling for silicon, the cost required to squeeze out each additional fraction of a percent in efficiency is becoming economically prohibitive. Since 2022, efficiency jumps have been hard-fought and incremental. The global energy transition requires that the cost of renewable electricity continue to fall. To maintain this trajectory, the industry cannot simply rely on building larger silicon factories. It must embrace an entirely new semiconductor material, capable of bypassing the physical constraints of silicon to unlock unprecedented levels of power generation. The urgent industrial mandate to shatter the crystalline silicon ceiling has catalyzed the rapid development of a revolutionary class of synthetic materials known as Perovskites. To the general public, the term Perovskite might sound like a newly discovered element, but it actually describes a specific, unique crystallographic structure. Originally named after the Russian mineralogist Lev Perovsky following the discovery of calcium titanate in the Ural Mountains, the term now encompasses a massive family of materials that share the same cubic atomic arrangement, typically represented by the chemical formula AbX3. In the late 1970s, a researcher named Dieter Weber at the University of Stuttgart achieved a major milestone by discovering the first hybrid organic-inorganic halide perovskite, successfully replacing traditional inorganic ions with organic molecules. It is these specific hybrid organic-inorganic metal halide perovskites that have completely revolutionized the modern field of photovoltaics. What makes these synthetic perovskite crystals infinitely more versatile than standard silicon is a profound optical property known as a tunable bandgap. As previously established, the bandgap of a semiconductor dictates exactly which wavelengths of sunlight it can absorb and convert into electricity. Silicon has a fixed, unchangeable bandgap dictated by the rigid laws of nature. It is moderately good at absorbing red and infrared light, but highly inefficient at capturing the high-energy photons found in the blue and green spectrums of sunlight.
Perovskites, however, are essentially customizable chemical recipes. By systematically altering the chemical composition of the A, B, and X sites within the crystal lattice, scientists can stretch or shrink the material's bandgap to perfectly align with specific, highly energetic portions of the solar spectrum. The chemical engineering involved is highly precise.
The A site of the crystal is typically occupied by organic cations, such as methylammonium or formamidinium, or inorganic elements like cesium. The B site generally utilizes a heavy metal, most commonly lead or tin, while the X site consists of halide anions, such as iodine, bromine, or chlorine. By precisely mixing these elements, for instance, increasing the ratio of bromine to iodine, researchers can widen the bandgap of the perovskite crystal.
The industry has aggressively explored numerous elemental substitutions. While researchers have attempted to replace lead with elements like magnesium, barium, calcium, or strontium to address toxicity concerns, these alternatives often exhibit unfavorable formation energies or excessively wide band gaps that make them poor candidates for solar cells. Conversely, introducing specific atomic structures, such as rubidium or potassium, has been shown to dramatically enhance the structural stability of the crystal lattice without sacrificing its exceptional light-absorbing properties. This incredible ability to customize the bandgap of a semiconductor has given rise to the holy grail of modern solar engineering, the tandem solar cell. The mechanics of a tandem cell are a masterclass in complementary physics. Instead of attempting to entirely replace the massive global silicon infrastructure, the tandem architecture stacks a microscopic, ultra-thin layer of customized perovskite directly on top of a conventional silicon solar cell. Because perovskites feature an exceptionally high optical absorption coefficient, this top layer only needs to be a few hundred nanometers thick, roughly 95% thinner than the silicon wafer beneath it. When natural sunlight strikes this two-layer device, the top perovskite layer acts as a high-frequency energy filter. Because its bandgap has been specifically engineered, the perovskite crystal eagerly absorbs the high-energy visible blue and green light photons that a standard silicon cell would normally waste as excess heat, converting them into electricity with extraordinary efficiency. Because the perovskite layer is physically engineered to be semi-transparent to lower energy light, the remaining red and near-infrared photons pass directly through the top perovskite layer completely unimpeded, where they are easily captured and converted into electricity by the conventional silicon cell waiting at the bottom of the stack. By elegantly dividing the labor of the solar spectrum between two perfectly complementary materials, the tandem solar cell completely bypasses the Shockley-Queisser limit that physically restricts single-junction silicon devices. The theoretical efficiency ceiling for a dual-layer perovskite silicon tandem stack reaches approximately 47%, a staggering number that opens a vast new frontier for commercial power generation. If multiple layers of varying perovskites are stacked together, theoretical thermodynamic limits suggest efficiency could push towards 60%. The transition from theoretical computer models to verified laboratory breakthroughs has occurred at a pace entirely unprecedented in the history of energy research. While traditional crystalline silicon required over 40 years of grueling engineering to climb from its initial practical applications to 25% efficiency, Perovskite technology achieved similar performance milestones in less than 15 years. By late 2024 and early 2025, the global race to commercialize tandem cells resulted in a flurry of shattered world records. The Chinese solar manufacturing giant LONGi Green Energy officially claimed the world record for a Perovskite silicon tandem solar cell, achieving a breathtaking power conversion efficiency of 34.85% on a standard test device. This milestone, rigorously tested and independently verified by the United States National Renewable Energy Laboratory, NREL, represents a massive leap past the theoretical limits of standard silicon. Furthermore, unconfirmed updates from LONGi indicate they have already breached the 35% efficiency threshold in internal testing, signaling that the technology is maturing rapidly. Simultaneously, competitors like Jinko Solar have demonstrated their own advanced capabilities, announcing a certified conversion efficiency of 33.84% by printing a Perovskite tandem cell directly onto an advanced N-type TOPCon silicon base. Even for standalone single-junction Perovskite cells without a silicon bottom layer, academic institutions such as the University of Science and Technology of China have achieved verified stable efficiencies of 26.7%, matching the performance of highly mature commercial silicon panels.
The science is proven. The materials possess the raw capability to redefine global power generation. The true challenge now lies not in initial efficiency, but in long-term survival. Translating these spectacular, record-breaking laboratory efficiencies into commercially viable rooftop solar panels presents a formidable mechanical and chemical challenge. In the commercial solar industry, there is a rigid, non-negotiable standard. A solar panel must survive at least 25 years of unrelenting exposure to the natural elements.
Silicon panels easily meet this standard because silicon is fundamentally a highly stable, purified rock. Hybrid organic-inorganic perovskites, however, are highly complex, delicate chemical structures that are notoriously vulnerable to environmental stressors. If a raw perovskite film is exposed to the ambient environment, it begins to degrade almost immediately. Moisture from basic humidity is a lethal enemy. Water molecules can rapidly dissolve the organic salts within the crystal lattice, causing the active photovoltaic material to literally wash away. Oxygen penetration can trigger severe chemical oxidation, destroying the charge transport layers. Furthermore, because solar panels are designed to sit in direct sunlight, they are subjected to intense thermal stress and relentless ultraviolet radiation. These intense temperature fluctuations, combined with UV exposure, can cause the organic components of the perovskite, such as the volatile methyl ammonium ions, to bake, evaporate, and structurally collapse over time. Perhaps the most insidious and complex threat to the 25-year lifespan of a tandem cell is a microscopic phenomenon known as ion migration. Unlike the rigid atomic lattice of a silicon crystal, a perovskite crystal features a relatively soft and pliable framework. When the perovskite material is exposed to intense sunlight and the strong internal electric fields generated during normal operation, the charged ions within the crystal, specifically the halide ions like iodine and bromine, can become physically dislodged from their designated atomic positions. These liberated mobile ions slowly drift and migrate through the soft lattice of the material, accumulating at the physical boundaries and interfaces of the solar cell. This internal ion migration causes devastating operational issues. First, it leads to a buildup of electrical charge at the boundaries, which unbalances the flow of electrons and creates a severe mismatch in the cell's voltage output, a crippling phenomenon known to engineers as hysteresis. Second, As the ions drift apart, the crystal undergoes phase segregation, meaning the carefully tuned chemical mixture separates into useless, isolated clumps of iodine and bromine, completely ruining the material's carefully engineered band gap and its ability to conduct electricity. During the manufacturing process, high-temperature thermal annealing can also introduce severe tensile strain into the perovskite film due to mismatches in thermal expansion between the soft perovskite and the rigid glass substrate, further accelerating this destructive ion migration. To overcome these immense durability hurdles and achieve commercial viability, the global research community has launched a massive campaign of chemical engineering to stabilize the perovskite lattice. Researchers have discovered that systematically replacing the highly volatile methylammonium cations with larger, more robust organic molecules like formamidium significantly enhances the thermal stability and evaporation resistance of the final crystal. To combat the destructive force of ion migration, scientists have introduced highly specialized chemical additives directly into the manufacturing process.
For example, researchers at the Chinese Academy of Sciences successfully introduced alkali metal oxalates into the perovskite ink. The potassium ions released by these oxalates aggressively bind to the migrating chloride ions, physically anchoring them in place and effectively suppressing their uncontrolled movement through the material. This chemical locking mechanism resulted in a solar cell that retained over 86% of its initial efficiency after more than 1,500 hours of continuous, rigorous operation.
Other critical advancements involve interface engineering and the use of green solvents. Historically, perovskite inks were dissolved using highly toxic and low volatility solvents like dimethylformamide. Traces of these harsh solvents would remain trapped within the dried film, acting as a slow poison that degraded the crystal from the inside out. By transitioning to specialized green solvent systems and utilizing two-dimensional precursor phase crystallization routes, engineers can completely evaporate the liquid carrier, leaving behind an immaculately pure, phase-stable perovskite structure.
These pure structures demonstrate incredible resilience, easily surviving advanced damp heat stress tests involving sustained exposure to 85 degrees Celsius at 85% relative humidity. Through advanced two-dimensional and three-dimensional interface engineering, institutions like the École Polytechnique Fédérale de Lausanne have achieved astonishing module stability, exceeding 10,000 hours of continuous operation. While laboratory stress tests are promising, the ultimate proof of commercial readiness requires passing the grueling, independent certification standards demanded by utility companies. Recent breakthroughs indicate the industry has finally crossed this threshold. GCL Technology recently unveiled a commercial perovskite silicon tandem module that successfully passed the rigorous international IEC 61215 and IEC 61739 testing standards. Passing these intense environmental and electrical stress tests serves as official validation that the tandem module degrades at a rate nearly identical to established, durable silicon solar modules. With the degradation challenge increasingly viewed as a solved engineering problem, the focus of the global industry has shifted entirely toward the high-stakes mechanical challenge of mass-producing these volatile chemical structures at a gigawatt scale. The transition from traditional crystalline silicon to perovskite tandem technology represents much more than a shift in semiconductor chemistry. It constitutes a fundamental, highly disruptive revolution of the industrial assembly line. For decades, the global standard for producing high-purity monocrystalline silicon has relied upon the Czochralski process. This legacy manufacturing method is intensely heavily industrialized, tremendously expensive to build, and shockingly demanding on regional energy grids. The physical reality of the Czochralski process is brutal. It begins with raw, metallurgical-grade silicon rock, which must be chemically purified in massive electric arc furnaces operating at extreme temperatures exceeding 1,900 degrees Celsius. This highly purified polysilicon is then placed into specialized crystallization chambers and melted into a liquid bath, a process that requires maintaining temperatures above 1,400 degrees Celsius for several consecutive days.
From this glowing molten liquid, a single massive cylindrical crystal ingot is meticulously and slowly pulled upward as it cools. Once this heavy silicon ingot is finally formed, it is subjected to intense mechanical slicing. Massive arrays of fine diamond wire saws physically grind their way through the solid crystal cylinder to shave off the individual, ultra-thin silicon wafers.
This brutal mechanical sawing process is inherently and unavoidably wasteful. Up to 50% of the highly purified, energy-intensive silicon crystal is simply destroyed, ground away into useless kerf dust. The entire sequential operation, from melting the raw quartz to producing a functional individual solar cell, can easily take over 72 hours of continuous heavy industrial processing, requiring specialized mega facilities that routinely cost billions of dollars to construct.
In stark, dramatic contrast, Perovskite materials belong to the realm of thin-film photovoltaics, bypassing heavy industrial smelting entirely. Thin-film manufacturing does not require extreme, multi-day high-temperature baking, crystallization chambers, or violent physical sawing. Instead, the highly precise chemical precursors required to build the perovskite crystal are simply dissolved into specialized liquid solvents, creating a highly active liquid photovoltaic ink. This liquid ink can then be rapidly applied directly to substrates using high-speed, highly scalable printing techniques, primarily slot die coating and chemical vapor deposition.
Slot die coating is a manufacturing technique originally perfected by the photographic film and newspaper printing industries. It involves pumping the liquid perovskite ink through a highly precise microscopic slit, the slot die head, which extrudes a continuous, perfectly uniform, ultra-thin layer of the material directly onto a rapidly moving substrate or glass sheet. The energy dynamics and speed of this thin-film manufacturing process are revolutionary. The entire slot die coating and subsequent drying process occur at remarkably low temperatures, typically well below 150 degrees Celsius.
Once the liquid film is applied, it crystallizes into a highly efficient, light-absorbing layer in less than 60 seconds, drastically compressing the manufacturing time compared to the days required to pull and slice silicon ingots. Furthermore, the material utilization efficiency is staggering. In advanced slot die deposition, over 95% of the perovskite ink is applied directly onto the functional substrate, virtually eliminating the massive, expensive material waste characteristic of traditional silicon wafer sawing. Because printing a solar cell requires a fraction of the heavy machinery and electrical heating required by the Czochralski process, the embodied energy and carbon footprint of global solar manufacturing can be drastically reduced. Consequently, analysts project that the manufacturing costs for perovskite modules could plummet to roughly 57 cents per watt, representing a nearly 50% reduction compared to the overall capital expenditures required to establish traditional crystalline silicon facilities. However, despite the overwhelming economic and environmental advantages of printing liquid solar cells, the global energy industry cannot simply abandon its legacy infrastructure overnight. Hundreds of billions of dollars in capital have been sunk into existing, highly optimized crystalline silicon factories distributed across the globe. Therefore, the current strategic pivot, rapidly accelerating as the industry approaches 2026, centers on the concept of retrofitting these legacy facilities rather than bulldozing them. Global solar manufacturers are actively developing additive thin-film assembly lines that can be physically integrated directly into the back end of existing silicon production plants. This hybrid retrofitting approach is highly strategic. By installing automated slot die coaters, inkjet printers, and vapor deposition vacuum chambers directly alongside traditional silicon finishing lines, manufacturers can take a standard, freshly manufactured silicon wafer and immediately transform it into a high-performance tandem cell with minimal disruption to their core operations. The process is highly sequential.
The base silicon cell is prepared, a whole transport layer is deposited, the perovskite ink is printed or evaporated onto the surface, and a final protective, transparent, conductive layer is applied to seal the device.
Researchers have found that utilizing advanced slot die coating techniques to apply these intermediate layers, such as depositing specialized whole transport materials like NiOX, dramatically improves the wettability of the surface, suppressing energy losses at the physical boundary between the silicon and the perovskite, ensuring maximum electrical flow. This massive industrial pivot has firmly bridged the gap between academic theory and commercial reality. Major operational milestones are actively being achieved in 2026 as specialized firms transition to pilot scale and commercial production. In the United States, startups like Tandem PV have successfully launched commercial demonstration factories in locations like Fremont, California.
This specific facility features 40 megawatts of annual nameplate capacity, validating the ability to print large format tandem panels that are roughly 60 times larger than the microscopic devices tested in university laboratories. By demonstrating accelerated lifetime testing that shows less than 1% average annual power loss, these facilities prove that the fragile chemistry of perovskites can be reliably mass-produced to meet strict utility-scale reliability standards.
Similarly, in Europe, pioneers like Oxford PV have brought fully integrated manufacturing lines online in Brandenburg, Germany. Oxford PV recently executed the first successful commercial shipments of perovskite tandem modules, boasting certified efficiencies of 26.9%, directly to utility integration partners, proving that the technology is ready for mainstream field deployment. Massive global corporations are recognizing this shift and entering the fray.
First Solar, the world's largest producer of thin-film solar technology, recently finalized a sweeping patent licensing agreement with Oxford PV to accelerate the integration of perovskite technology into their massive automated manufacturing plants in the United States. However, as the bottleneck of heavy machinery is solved by the elegance of high-speed printing, a severe underlying geopolitical tension is rapidly emerging. The success of an entire gigawatt-scale printing factory is now wholly dependent on the reliable procurement of highly specialized, atomic-level raw materials, shifting the balance of global energy power.
As the fundamental physical architecture of the solar panel transitions from a solid rock to a printed chemical film, the map of strategic global dominance is being completely redrawn. For the past 2 decades, the geopolitics of the solar energy industry was largely a brutal game of silicon and silver scarcity. Nations vied aggressively for control over the mining of metallurgical-grade quartz and the immense regional electrical grid capacity required to melt and refine it into polysilicon. With the dawn of the perovskite tandem era, the strategic high ground has abruptly shifted away from heavy mining and toward the hyper-concentrated control of advanced chemical precursors and highly specialized glass substrates. To physically build a tandem solar cell, manufacturers absolutely require specialized glass coated with a thin layer of transparent conductive oxide, TCO. Because the perovskite layer is printed directly onto the panel, this front glass cannot be standard window material. It must utilize specific coatings, such as fluorine-doped tin oxide or indium tin oxide, ITO. This specialized TCO glass acts as the crucial front electrode of the entire device, simultaneously allowing maximum sunlight to penetrate into the active perovskite layer, while capturing and conducting the generated electrical electrons away to the power grid. Currently, fluorine-doped tin oxide accounts for over 62% of this specialized glass market. The global supply of this critical material is tightly controlled by a small handful of massive glass conglomerates, heavily concentrated in the Asia-Pacific region, which currently commands over 44% of the global market share. Furthermore, the active light-absorbing layer of the solar cell itself relies entirely on a steady, uninterrupted supply of highly pure organic halides. Formamidinium iodide, the crucial stabilizing organic salt used in the latest generation of durable perovskite crystals, has suddenly become one of the most highly sought-after chemical precursors in the world. The purity of these chemical ingredients is absolutely paramount to the survival of the final solar panel.
Studies have proven that microscopic impurities inadvertently introduced during the chemical synthesis of these precursors, such as rogue acetate molecules or excess potassium left over from the refinement of lead iodide, can trigger catastrophic, rapid degradation and completely ruin the operational efficiency of the printed Tandem module. As a result, securing ironclad, long-term supply contracts for ultra-high purity formamidinium iodide is the primary operational hurdle for emerging tandem manufacturers. Currently, the supply chain for these hyper-pure chemicals is heavily centralized.
Japan leads the world in producing ultra-pure, certified formamidinium iodide for high-end research applications, while nations across Southeast Asia, such as Malaysia and Vietnam, are rapidly expanding their local chemical supply chains to support their growing domestic module assembly hubs. The stark reality of the 2026 market is that whoever controls the large-scale refinement and synthesis of these specialized atomic-level chemicals essentially dictates the absolute speed at which the global perovskite industry can safely scale.
The desperate urgency to domesticate these critical chemical and glass supply chains is deeply rooted in severe industrial trauma. Western policymakers vividly remember the devastating supply chain shocks that nearly destroyed their domestic energy sectors in the early 2010s. During the late 2000s, an intense global shortage of polysilicon drove raw material prices to astronomical heights, peaking at over $400 per kilogram. Responding to massive European and American demand, Chinese solar manufacturers initiated a period of aggressive, debt-fueled expansion, heavily subsidized by state financial support, rapidly building out massive domestic polysilicon and wafer factories. China's share of global photovoltaic cell production surged dramatically from just 14% in 2006 to over 60% by 2013.
However, when the 2011 Eurozone financial crisis struck, European governments immediately gutted their lucrative solar feed-in tariffs, sharply and suddenly curbing global demand for solar panels. The global market was instantly flooded with a massive oversupply of deeply discounted Chinese panels, initiating a brutal pork cycle that caused the spot price of polysilicon to crash violently, eventually plummeting below $10 per kilogram.
This sudden, devastating price crash decimated the established solar manufacturing sectors across the United States and the European Union, triggering a wave of bankruptcies that wiped out early industry titans and shuttered hundreds of factories. The crisis peaked in 2013 with the spectacular collapse of global solar giants like Suntech and LDK Solar. Recognizing the strategic value of the industry, the Chinese government intervened, salvaging their domestic sector through aggressive internal installation targets and state-backed restructuring.
By surviving this internal shakeout, Chinese firms consolidated their power, ultimately establishing the undisputed, ironclad monopoly over the modern silicon value chain that exists today. Determined to absolutely prevent a repeat of this disastrous history, global powers are now aggressively wielding national subsidies, massive tax credits, and highly protectionist trade policies to artificially create localized solar valleys within their own borders. The United States, propelled by the sweeping manufacturing incentives embedded within the Inflation Reduction Act, is funneling tens of billions of dollars into domestic clean technology production.
To protect this nascent domestic supply chain, the U.S. government has implemented strict foreign entities of concern rules and levied harsh countervailing duties on imported components. Recently, the U.S. Department of Commerce expanded these tariffs significantly, cracking down on tariff circumvention by imposing massive duty hikes on major producers operating in Southeast Asia. For example, investigations uncovered that solar producers in Thailand, such as Trina Solar and Sunshine Electrical, were receiving illegal cross-border subsidies from China in the form of heavily discounted wafers, solar glass, and silver paste, resulting in immediate tariff increases of 13 to 39%.
Similarly, the European Union has activated powerful mechanisms within its Green Deal and Net Zero Industry Act to shield its remaining domestic producers from what it views as heavily subsidized foreign competition. Haunted by the collapse of their original solar sector, the European Commission has even launched preemptive anti-subsidy investigations into Chinese battery electric vehicles and wind turbines to prevent a repeat of the 2012 solar crash.
Europe views the Perovskite tandem revolution as a rare, highly strategic second chance to reclaim its technological sovereignty by funding massive research consortiums like the Pepperoni Project and establishing advanced industrial pilot lines in regions like Brandenburg, Germany. The EU is attempting to rapidly localize the production of next-generation thin-film solar technology before external monopolies can fully pivot their massive manufacturing bases to the new standard.
Concurrently, China is not remaining idle. The Chinese government has formally recognized perovskite technology as a critical pillar within its 14th five-year plan and emerging industry strategy. Facing intense involution, a term used by the Chinese government to describe the fierce, margin-crushing internal competition and overcapacity currently plaguing their legacy silicon sector, Chinese firms are aggressively pushing the boundaries of large-area perovskite efficiency. By mobilizing vast state resources, fostering high-tech university spin-offs, and scaling gigawatt-level pilot plants, China aims to ensure its undisputed dominance seamlessly transitions from the era of silicon rock to the era of printed chemical inks. This fierce, high-stakes geopolitical competition to secure the perovskite supply chain is not simply about corporate market share. It is fundamentally tethered to the broader macroeconomic goal of achieving the lowest levelized cost of energy in human history.
The levelized cost of energy is the ultimate metric of the power industry. It dictates the final, bottom-line price of electricity generated over the entire lifespan of a power plant, factoring in all initial capital costs, operational maintenance, and total power output. Currently, traditional silicon installations command an LCOE usually between 5 and 12 cents per kilowatt hour, depending on the specific regional market conditions. While initial low-volume perovskite modules currently exhibit a higher LCOE, roughly 18 to 22 cents per kilowatt hour, the inherent economics of their manufacturing dictate a massive future price collapse. Because perovskite tandem cells promise to deliver vastly more power per square meter while utilizing a slot die printing process that requires dramatically less energy and capital to build, they hold the explicit mathematical key to permanently breaking the current floor on global energy prices. The nation that successfully secures a sovereign, uninterrupted monopoly over the high-purity atomic-level chemical precursors, the specialized TCO glass substrates, and the high-speed thin-film manufacturing equipment will effectively dictate the fundamental economics of the entire 21st century. By driving down the baseline cost of bulk electricity lower than ever previously imagined, that victorious nation will gain an absolutely insurmountable competitive advantage in every single adjacent industrial sector that relies on massive power consumption. From the operation of sprawling artificial intelligence data centers to electric vehicle manufacturing and heavy industrial steel smelting. The transition away from the rigid, crystalline silicon ceiling marks the beginning of a profound, irrevocable transformation in how the human race harvests power from the sun. The global scientific community has successfully engineered its way around the rigid thermodynamic laws of the Shockley-Queisser limit by mastering the complex, tunable bandgaps of synthetic perovskite crystals. The heavy, energy-intensive industry of solar manufacturing is aggressively pivoting away from the brute force methodology of melting and sawing quartz, moving toward the high-speed, hyper-efficient elegance of printing chemical inks. However, the ultimate long-term success of this monumental technological leap relies entirely on navigating the highly perilous geopolitical waters of supply chain security.
As the world frantically races to retrofit its legacy factories and deploy the first commercial tandem solar panels into the field, the nations that can successfully master the complex, delicate interplay of chemical refinement monopolies, strategic protectionist subsidies, and advanced thin-film manufacturing will secure the sovereign power to permanently fuel the global energy transition for decades to come.